All right. Okay, we have Chethan Krishnan from CHP ISC to talk to us about bottom-up approach.
Yeah. Let me start by thanking the organizers for this nice conference and also for letting me speak here. So this is a talk that I more or less gave a few weeks ago, and many of you were there in the audience in Pune, but I thought I'll give it again here because I think at least a substantial fraction of the audience is different, and there are experts I can see in the audience who might have more to say about it. So because it might be a little controversial, so let's see how it goes. So yes, so this is, so I'm going to give you like a kind of an overview of a few different papers written over the last few years. Maybe 2 years. And so I'll mostly focus on these two papers which came out at the end of last year and some few things that are coming out maybe in the next few days or weeks. And also some older papers with, and those were written with my students Vaibhav and Pradeep who are in the audience. And so Chethan is a postdoc who has just now moved to Calcutta. And also this started off with some work with Arnab and various friends. And it's like, I will not have much to say about those things today, but that we kind of came to these things by a roundabout route. So now I think we understand a little bit better. So, so that's where we'll start. So let me start by saying that, horizons necessarily have an entropy of A/4gh, as we all know. And so it means that if the horizon is part of the description, there is no way to avoid having unaccounted for entropy. Okay, so this may be or may not be controversial, but I think it is a fair statement. So the bulk description of a black hole microstate cannot by definition contain conventional horizons. So this is the first slide. So the reason why it's good to think about that way is because sometimes we would like to understand microstates as a way of understanding information paradox. An information paradox is fundamentally a Lorentzian problem and not a Euclidean problem. And so we would like to not just answer it in terms of Euclidean path integrals and amplitudes, or at least if you're thinking about it, entanglement entropies and so on, it's combinations of matrix elements and such. But instead, we would like to really understand it in terms of some Hilbert space states, very roughly speaking. So, so that's the sense in which we would like to understand microstates, and it's probably necessary to have a fully satisfying understanding of the information paradox. Okay, so currently, we do not have a top-down construction of such typical finite temperature black hole microstates in string theory. So the ones that have been constructed are typically extremal or BPS, and it's not even clear whether they genuinely capture black hole microstates or just some multi-graviton states. So clearly this question is open. So one thing I would say about fuzzballs here is that at least they show that there exist mechanisms in string theory which can evade no-hair theorems. Okay, so that's the sense in which, that's the only sense in which I will really need fuzzballs. So, so given the state of affairs, we can ask, can we engineer an instructive picture? Instructive is the key word there. So picture of bulk microstate using bottom-up arguments. So this is the question that we would like to ask. And I really want to emphasize instructive because by definition, if it is bottom-up in the sense of from infrared to ultraviolet, I mean, it may not be, there has to be a sense in which I have to defend that it is useful for some UV stuff. Okay, so that's where we will begin. So, so the possible demands that we can impose, our first one is, as I said, we want it to be in Lorentzian signature, and we want it to be away from supersymmetry and extremality because, as I said, in order to really formulate the information paradox in the kind of the conventional setting, we want it to be at finite temperature. And we also have some intuition for bulk states in ADS-CFT. And so we would like to work in ADS-CFT, not in flat space or something where, I mean, there are things we understand about flat space in string theory, but its ADS-CFT clearly gives us a non-perturbative definition, and the questions that we have to understand seem like, they're intrinsically non-perturbative, so maybe this is a better place to start. And finally, it seems reasonable, to try to understand the black hole itself and not treat it as an open system to start. And so in that sense, I will be looking at large ADS black holes, and presumably something that we understand there can actually be transported to, let's say, a finite, an evaporating black hole in flat space eventually. This is the hope. Okay, so, and yeah, so our first natural target, therefore, is to try and get a bulk picture of a heavy microstate in the CFT. And these are the microstates of a large ADS black hole. Okay, So what can be a bottom-up way to engineer a heavy CFT microstate is a question that we will ask. So the first thing we would consider, so essentially like it is some stretched horizon type of setup that I will talk about. So to, not to, to pull any punches. So, but the question is how should we completely give up the metric if we are trying to start with some microscopic, some sort of microstate construction. So, and that's a reasonable guess because, as we heard today morning in the very nice talk of Gautam, that finite end physics seems to kind of discretize everything. So that's maybe after all, looking for finite end physics, we are looking for finite Planck length physics in the bulk. So, but this is clearly, if that is the case, then there is no hope of any kind of bottom-up type of thing that I'm talking about. But the metric description by itself is not what is causing unaccounted entropy and possibly the information paradox. So maybe it is reasonable that you can come up with, some ingredients that are sufficiently well put together that they can be instructive about the UV. Yeah, sure.
The horizon is, of course, only a semi-classical concept.
Correct.
And the fact that you can see past the horizon if you do very fine measurements, that's consistent with the fact that when you write down the expectation value of the metric, there's a horizon. So there isn't really a sharp contradiction here. I mean, of course, one can find solutions, maybe, which is what you'll do. But
no, but so if you have a microstate, I mean, if you do very, very fine measurements, I think you would change the state, right? So
the state to have a horizon, right? Pure
so are you talking about my first slide? So are you saying
this one
that
also, like the horizon is causing a, somehow the horizon
right.
is the problem.
So what I mean by that is that can we have a metric description? That's what I'm meaning here. So if we just have a metric description, you need not have unaccounted entropy. That's all I'm really saying here. So if you have an ADS geometry or even like a, some excited state which is not too heavy, you can expect to have like a bulk metric description, right? So, but on the other hand, you no longer can afford to do that if you also have a horizon. That's basically the statement I'm making. So if you want to have, the geometry has to not be a metric description, at least by the time you get to the horizon. That's necessary. This is the statement.
Classical description, because quantum mechanically we know there's no no-hair theorem. So no-hair theorem is only a classical problem. So you want, here you're going to insist on a classical description.
No, I'm going to insist on some kind of, you'll see. It's basically, actually I will be constructing explicit states in a Hilbert space and not, like in the sense of, see, one of the things about fuzzballs is that it's basically classical coherent solutions. Even if, assume that they were microstates of the black hole, in some sense. But the problem in some sense to me is that they're coherent states. So it's not so easy to formulate questions like how a smooth horizon might form. So it would be nice to have a convenient basis where you can phrase this question so that you can phrase the question of smoothness and so on and so forth. So yeah, so anyway, so the statement is that we are trying to look for something that captures finite end physics in the bulk, but we want to retain only as much, we want to discard only as much as we have to. So this is the way in which I'm looking at it. So is there a way to give up only the horizon in a meaningful way? So I mean, you can decide whether at the end whether it is meaningful or not, but giving up the metric everywhere feels like, entire space-time is on fire suggestion, which I think is ultimately where string theory will head us if you have a truly finite end statement. And I also should say that, because there was one question that was asked at some point, that, if you, it's also possible that, your dual description, so if non-perturbative string theory, if it only has a holographic description, none of this is really very meaningful. So I'm assuming that there is some bulk finite end description, which I think, for instance, again, Gautam's talk kind of tells you that there could be. So that's actually also a thing to keep in mind. So, yeah, so with this prejudice, one thing that you could do is that so clearly we want to discard the horizon in some way, and the oldest idea is of this that I know, where this was explicitly tried for the purposes of this, is a paper by Toft. There are some membrane paradigm type of ideas around, but I would say that this is the place where he was really genuinely trying to discard the horizon deliberately. And so, I mean, there are problems with it and so on. So I will try to argue that seems like there is one, you can see whether there is a way in which it can be managed. Okay, so back to our question, is there a way to give up only the horizon in a meaningful way? And there are two hints, because we are in a fairly concrete setting, because we are in large heavy states in large black hole states in ADS-CFT. So a heavy microstate in ADS is in equilibrium with its own radiation. So this is one fact that we know, because that's the way we think about it. So we cannot simply replace the horizon with, say, a Planckian stretched horizon, then call it a day. Okay, so that we cannot do. Because oftentimes when people talk about stretched horizon, they just cut off the horizon and then leave it at that. For instance, if in many of the, in the calculations, of gravitational waves, all these recent GR calculations, where people try to see whether there is modifications of general relativity, what they do is oftentimes they just truncate the space-time around the horizon. But I don't think that's a fully satisfactory way to do that if you're looking for a realistic, or at least something that has a chance of being realistic modification of a black hole or black hole microstate. And so the reason is ultimately that when you remove the horizon, you lose temperature, you lose all the features that you expect from a thermal object, and they might be fundamental. So, and secondly, and importantly, there is always a large negative stress tensor at the stretched horizon. This is a well-known fact, and it has some name in QFT in curved space. And this is roughly speaking the idea that if you install a stretched horizon, it's always trying to pull things in, right? So you will have to kind of expend some energy to stay where you are, and that's basically what this is, okay? So, but the crucial thing about it is it's a negative stress tensor. And the price for violating equivalence principle is essentially what that is. And so how are we going to, let's say, avoid doing that is the question. So it has been suggested, and this is, I think, an interesting paper. It doesn't have many citations, but, some number of citations. So is a paper by Israel and Yukawa, which I think is very interesting, is that they've suggested that you should dress the system with radiation. Okay, so that if you dress the system, like you remove the stretched horizon, and they were trying to legitimize the construction of Toft. And in the paper, they say that Toft himself was hesitant to kind of take it seriously because of various issues, like the issues that they are solving in some sense. So, and the idea is basically that if you dress the system with radiation, then it essentially cancels this negative stress tensor, and you can then potentially, at least that's a viable model, or they do some heuristic calculations in their paper which show that, okay, at least these things seem to cancel. Okay, so this is the kind of calculation that they do. So what is remarkable, or at least what I find remarkable, is that both of these problems are simultaneously solved by the same ingredient, which is radiation. Okay, so it's a very qualitative fact, but at the same time, I think it is, one should not ignore those facts. So radiation is precisely what was missing when we simply install the stretched horizon model for a heavy CFT microstate, and if you add them, apparently, it can get rid of this, this Boulevard vacuum kind of problem. So, so in our papers, what we are essentially doing, so now I think I'm basically making the main statement, which is that in our papers, we argue that if you interpret the radiation as a highly excited state in a quantum field theory living on this ADS with a stretched horizon, then that could be a model for the radiation, and the states of this radiation are qualified, as we will argue, as the microstates of the black hole. So this is the let's say, the bottom-up model that we are putting forth. This is, it's basically a QFT in ADS with a cutoff, and it's an excited state. And I think you asked me this question previously, and I still don't have an answer. So, you're asking where the localization of this thing is. It's still not clear to me. That's the, yeah.
Also, if you measure correlation functions in the bulk as you approach the horizon, Boulevard vacuum doesn't only have a singularity, it also has a 1/r to some power divergence. Yes. So if you
so that will be cancelled by this radiation.
But will it be exactly the same?
No, it will not be exactly the same, but so this calculation in 1+1 dimensions is what is basically done by Israel and Mukuyama. Okay. So in order to properly do it, we have to do the stress tensor expectation value in our highly excited typical state. Good. So I expect that it will have like it can have some order 1 effects, or maybe even smaller. It can even be smaller, I think. But I'll have to actually do the calculation.
I see. But then we're in trouble, right? Because for a typical microstate, we know that it should look exactly like a thermal state.
Yeah, but I think you will see that. So there is a large n limit. There is a sense in which the correlator becomes exactly Hartle-Hoffman. So that's one of the things I'll say. So this is, can I use this? Yeah, it looks suspicious. Okay, I'll keep it here. Okay, great. I won't die. Okay, I think it is new. Thanks. All right, so, yeah, okay, so the main statement is that it's not the stretched horizon vacuum that should be compared against this black hole microstates, but a typical state in the Hilbert space with energy, which is asymptotically measured at the mass of the black hole. And so the point here is that, so we are kind of compensating two problematic features against each other. One is that if you just remove the stretched horizon, everything wants to fall in, and there is negative divergence and so on, as Suvrat was saying. But then there is also the problem that if you just put a highly excited state, there is a huge back reaction, right? So what this is sort of doing, or at least this is the way I'm thinking about it, which is that these two problems are sort of canceled against each other, and then you have a regulator which is, the stretch horizon is essentially acting as a regulator, and at the end, except for this one parameter freedom that you will see coming from the location, roughly speaking, of the stretch horizon, the rest of the things can be sort of fixed. So these excitations are radiation, and just demanding that the energy measured asymptotically is the black hole mass fixes the ensemble. So that's another point, which is that if you fix the energy at infinity, it basically fixes my ensemble, and that is enough for me to determine the temperature and entropy, except for this one parameter freedom that I mentioned. So the area scaling of entropy is a direct result of, so this is a somewhat surprising fact, at least it was for us, which is that this area scaling of entropy, typically if you put a cutoff in the bulk, let's say in flat space, or even in ADS, if you put a cutoff in ADS and if you compute the normal modes of the system of the field theory, what you will find is that essentially the J dependence and the N dependence, they both just goes linearly up, and you don't get anything that, so essentially what you're left with is a Planckian volume scaling, because all spatial directions are contributing one n of the harmonic oscillator each. So if you have nx, ny, and nz in flat space or in ADS, you will find that there is a each of them will contribute one n for the harmonic oscillator. So in the end, you will find a volume scaling. But what happens here is that this scaling of entropy is actually an area law, and this was the observation ultimately, going back. This is the thing that Toft was the first to notice, even though, it was not, I don't think it was very clear from his calculation why that happened. Maybe there are experts in the audience who knew that, but we didn't know why it was happening. So, and the technical reason why that is happening is because along the Casimir direction of the sphere, the quantum number, the Casimir quantum number of the sphere, there is very weak dependence of the spectrum, the normal mode spectrum, on that quantum number. And that is essentially, essentially instead of getting a volume law, you get one quantum number less, and because of which you end up getting an area law. So, and that's what happens here. And what we are doing is we are explicitly computing the normal modes instead of using the semi-classical calculation, a certain kind of semi-classical calculation that Toft did. So anyway, so there is, so this is the point. And so once we choose those certain, this one parameter freedom that I mentioned, and I can tell you more about it. So because it's an outline of many these things, you can talk to me afterwards, the precise way in which it is fixed. So the temperature also comes out correctly, and that's one useful thing, because typically what happens if you in the calculation, okay, I'll talk more about comparison with Toft maybe later. So the point is that in Toft's calculation, he has to specify both the energy and the temperature, because he did not compute the normal modes explicitly. So it's a somewhat unnatural calculation in the sense that it requires, it's not specifying an ensemble and getting the answer for all the other thermodynamic variables. So because we are computing the normal modes explicitly and just treating them as statistical mechanical system, we can just specify the mass, and both the entropy and the temperature come out automatically. Okay, so yeah, now I don't have to explain the difference from his calculation ours. So this can be viewed as some sort of an improvement on Toft's brick wall calculation. And this is what kind of motivated us to look at actual correlators, because otherwise you can't really formulate the question of correlators in a clean way. So the fact that both the entropy and temperature can be obtained correctly encourages us to compute the correlation setting and try to connect them with the thermal Hartle-Hawking correlator. And so basically what we do is we quantize fields with Dirichlet boundary conditions. And the Dirichlet condition is not very important as long as the condition is close enough to the horizon. And then you consider typical states E equals to MBH, and these states will be our models for black hole microstates. So then we look at extrapolate. I'm giving you a small outline of the thing, because after that it'll be, there might be some equations, and not too many, but there'll be some equations. I just want to give you an outline in the next few slides. So yeah, basically we compute these extrapolate bulk and boundary correlators, extrapolate boundary correlators as well bulk correlators, and we find that the stretched horizon to the, when we send the stretched horizon to the horizon, which essentially, as you will see, the finiteness of the stretched horizon is directly related to the finiteness of G Newton and finiteness of N and so on. So it is very naturally interpreted as a large N type limit. And in that limit, the stretched horizon correlators turn into the Hartle-Hawking thermal correlator is what we see. Okay.
One correlator is a 1-point function of the metric. or one-point function of the Riemann tensor.
Yeah.
And are you saying that becomes exactly that of the black hole geometry?
We have not computed the metric expectation values. We are mostly working with scalars. So the scalar excitations are what we are looking at, but it has enough freedom. So one of the ways in which, so this one parameter freedom is a very interesting one parameter freedom that we find. So it can incorporate having multiple fields. It will just, change the location of the stretched horizon and compensate for that by the number of fields.
And you see, you want the correlators to become the same as the correlators in the black hole geometry.
Right.
In particular, correlators of the metric, including its classical expectation value. So you see that because we need that. So then there's a there's some tension between making it look like the black hole and not having a horizon.
Right. See, but we are fixed. This is quantum field theory in curved space, right? With some sort of souped up quantum field theory in curved space. It's not a system where the metric is at the moment dynamical. Right? So we are working with, the background is basically still the black hole. And so the metric fluctuations are not yet meaningfully defined.
The scalar field and use that to get the local metric because they depend on geodesic distance. So,
and it depends on that in exactly the same way that it will depend in the standard Hardt-Locking correlator, right? And that it does. So the point, however, is that, but your question is still, I think there is something interesting there, which is in the sense that, ultimately, we would like to also understand how metric fluctuations behave and so on and so forth. So, so those things, it's, that's why this is still not, it's not a UV, this is definitely a bottom-up kind of thing, and to what extent it is useful, one has to see. Okay, so this is the statement. It's a Hardt-Locking correlator, usually viewed as an indicator of smoothness before the page time, and its immediate consequence of smoothness in Kruskal coordinates is how you get the Hardt-Locking correlator. So that's the reason why we are using it as an indicator of smoothness. But I should also say that by construction, our correlator is only on the right wedge of the two-sided. If you want to think of it as a two-sided black hole geometry, if you think of it as a one-sided CFT, it's only the right side that we are starting with because those are the regions where the geometry is defined. And then but then as you will see, there exists an analytic continuation that naturally emerges in the epsilon going to zero limit across the horizon. So okay, so this is so these are two reasons. As Suvrat was mentioning, so this Hardt-Locking correlator, for instance, is there are multiple reasons to think that that's an indicator of smoothness in a certain sense at least. Okay. So, and another comment, which is, again, there is a lot to be said here, but I'm kind of summarizing various things. So, essentially, the point is that, what is the sense in which you can talk about, this is a paper of Onkar and friends, where they note that, building on previous work, that if you have a thermal state and you'll probe it with small operators, then you essentially find a second tensor factor automatically arising. So what our calculation can sort of be viewed as this realization of this, together with one extra ingredient, which is that there is an emergent analytic continuation into the interior, even though at no point have we demanded an infalling boundary condition. Okay, so that's the statement, and I tend to think of it as a bulk version of this type 3 algebra transition, but type 3 is just a word for me, so I will leave it there. So I'll say a bit more about that eventually. Okay, so slightly more explicitly, let's work with BTZ, but we can actually generalize it to some other black holes also. The reason why we work with BTZ is because the wave equation is simple, and the problem of finding normal modes becomes numerical only at the sort of the final stage. So if you work with the wave equation of higher dimensional black holes, you have to solve various Hoyne equation type of things, and it's already numerical from the start, and we want to avoid it as much as possible, but I don't think there is a serious technical problem in generalizing it to higher dimensions. Okay, so the normal modes are basically defined by this equation. Again, as long as, you can have more general boundary conditions here, but as long as they are non-dissipative, doesn't seem to matter. And so the key technical fact is, in some sense, that this normal modes, you can determine them. I should probably draw a picture. So this is my normal modes, and this is the J. And roughly, these guys look like this. So this is the structure of the normal modes. And the expression that I have written there is a low energy approximation, which is valid in some region. but it is, there is some j, only till some j max it's valid, and it diverges. So this is, if I were to write it for n equal to 1, this is what it will look like. But the key point is that somehow it's only these modes. You will see that, so only the modes in the low-lying part of the spectrum basically contribute to the entropy, so we can work with an analytic approximation. So what essentially that means is that, so the reason why I'm drawing these as continuous is because if you look at that expression, you will, after a bit of thought, you will realize that the j spacing is exponentially smaller than the n spacing, and these are the n's. Okay, this is n equal to 2, 1, 3, etc. Sorry, 3, 1, 2, 1, etc. And this is the j spectrum is very dense, and that's what carries the entropy eventually. So, and one more thing was worth making a statement about is that in 1+1 dimensions, in Rindler, for instance, you don't get this j degeneracy. This degeneracy is crucially a property of the transverse, having a transverse sphere or circle. So, so this is, so I will basically, so the key thing that, the reason I showed you that formula is basically because it, if you look at the leading behavior the behavior in J can essentially be treated as degenerate, and the dependence on N is linear. Okay, so that's the only thing that I really need. And that's the only thing that I will basically need in order to make all the statements in this talk. But there is, of course, there is a lot of information inside the actual normal mode, omega nj's, and we have done some preliminary calculations. Sort of that's the way we came to it. Actually, is that you can see some linear ramp and level repulsion and some basic features of RMT that one might expect in this thing. But I don't want to make a very strong statement about it, because those are first quantized omega nj properties, and ultimately we will be interested in the level spacing of this field theory. So that we have not done yet, but we'll see. So anyways, so yes, we get a discrete, because you are putting a cutoff, right? So instantly there is no infall. So that's the point. So the boundary conditions are not infalling boundary conditions, but we can get eventually in the epsilon going to 0 or n going to infinity sort of limit, you find that they become the Hartle-Hawking correlator. That is the statement. So okay, so let me just show you the setup of the calculation. I will actually not show you the calculation, but essentially what we are doing is very simple. Once you put the cutoff, we just quantize a free scalar field in this background. And you should think of the free scalar field as a stand-in for some single trace operator in the gauge theory and so on, light single trace operator. And this is our modes. You can expand it, and then you find, so then the vacuum, the stretched horizon vacuum is defined in this way, but we are not interested in the stretched horizon vacuum. We are interested in these highly excited states in the Hilbert space of this quantum field theory. Okay, that's what we are interested in, because we want to get the mass of the black hole as seen from the boundary. So, okay, yeah, that's fine. No, so the point about this, on the other hand, is because it's a free theory, and because we are working with BTC where the wave equation is solvable, essentially everything except this omega nj that I showed you a low energy approximation of are analytically calculable. But I mean, you can, even though it's not analytically calculable, you can actually determine them numerically to quite some precision. And Pradeepta, my student, has done a lot of work on that. So, and that's our setup. And then we compute this boundary Whiteman correlator in the state. And so we look for states of, this is the place where the Schwarzschild mass goes in, and we get a typical such eigenstate, and this is what we call a microstate. We compute the Whiteman function there. Okay. So I didn't show you how we compute the entropy and the temperature. I mean, it's there in our papers, but it can be done. So, and this is the object that we can directly yeah, go ahead.
In particular, the modes that are largely occupied are the ones which have omega much smaller than the temperature.
No, actually no. So what happens is that, see, there is a, so yeah, so this is an important point, which is that, so if you look at the Toft calculation, what happens is that there is the way he computes it. So this is your angular momentum barrier, okay, and this is where you're putting the stretched horizon, let's say. So he is counting these modes, okay, the modes which are trapped behind the angular momentum barrier, if you like. So these are somehow semi-classical modes, and our prejudice is that those are not the fundamental objects. Okay, so our prejudice is that the true normal modes of the system is what you need to compute. So which means we're just solving the wave equation, and these guys, for instance, are not aware of tunneling. So that's why he was using some kind of a, I'm getting to your, to answer your question. So the point is that when you compute the normal modes, there is, so the angular momentum barrier, what it really did for him is that it gives you a cutoff in the J quantum number. And that J quantum number cutoff was crucial to make the entropy finite. Otherwise it diverges, because we are assuming that J is degenerate, right? So no matter how high our, so it doesn't, if the J, we're not keeping track of the slope of J, there might be some improvement if there is, the J slope is kept in this thing, but I fundamentally think that the J cutoff is coming from some stringy type of thing. So what we are doing is we have an epsilon coming from the stress horizon location, and then there is a J cut which we have to put in by hand, because we are not, we are not looking at the semi-classical modes, we are looking at the true normal modes. And but the interesting thing is that even after you put those in, it's only one combination of these two things that actually goes into the determination of all the parameters. So there is a sense in which there is, so what I said about a one parameter freedom is actually a combination of J cut and epsilon that is actually fixing everything. And if you fix that using the match with the coefficient of A by 4G, then you get the temperature also correctly. So this is the statement. So now maybe you can ask the question again. Yeah.
Expectation value of B dagger B for an omega.
What is V?
B is your creation operator that you had.
Okay.
So you had a B omega.
Okay.
So you could compute B omega dagger, for instance, expectation value of that. You know that has to look like 1 by 1 minus e to the minus beta omega, because that's the boundary answer.
Yeah.
And so that tells you that, unless you have unless 1 by 1 minus beta omega is going to 0, that is, you just have one occupation in that. So you know what the expectation value of the occupancy is, because you know that from the boundary.
Sure, yeah.
And so you're able to match that? And
yeah, I mean, in fact, what I'm saying is in some sense even more, right? I'm saying that if you fix the energy, the occupancy is completely fixed. Or at least there is a huge degeneracy of states which correspond to this condition that I'm putting. This is a boundary condition. You could think of it as a boundary condition, because this omega nj is seeable from the boundary, right? Because it's a time coordinate, everything is outside the horizon. That's the advantage. So in that sense, the energy that I'm measuring is literally the energy that I can see from the boundary. And once I specify that, the claim is that you get an explicit correlator. And once I get that thing, and then I send epsilon to 0, automatically I find the hard locking correlator. This is statement. J is the angular momentum quantum number. Yes.
Okay.
Yeah. So I'll have some comments about. Yeah. So this is, I think, yeah. So thanks for that question, because it's a particular combination of these two things that show up in the calculation. So now I'm not showing you anything, but I can just tell you what the sort of the punchlines are. At this stage, we can take epsilon going to 0 limit. The limit is well defined, and the result is the hard locking correlator in the outside. And so yeah, there are some technical facts which I'm not emphasizing, but I want to emphasize that once you make this particular setup, and the calculation is completely, it's just, there's nothing. Everything is completely determined. And at the end, you finally find this result. So the hard locking correlator dries as e to the minus pi t by beta, as we all know. And there is information paradox kicks in at the page time. This is Malasena. And but the point is that we are looking at these typical occupancies, because we have a level which is highly populated. So there's a notion of typicality in this high-lying state. And because of which, there is a natural notion of microcanonical suppression. Okay, so, and that automatically tells us that this correlation function has this e to the minus SBH by 2 kind of suppression. We can compute things, and then we show that, precisely at, and that matches, that coincides with this e to the minus pi t by beta precisely at the page time. Yeah.
Confusing me is that it seems to me you're just counting a gas of particles. And where you put a cutoff on the angular momentum.
That's correct.
So there's a gas of particles which is in fact propagating in the bulk. Why do you get the correct scaling between the entropy and the energy? I mean, it's just a gas of particles. You fix the total energy. Of course, you can count the entropy. It's just a Fock space. But there's a specific scaling that the black hole has between entropy and energy.
Yeah, which is precisely what we find. And I think that is happening because, this is the old observation of 't Hooft, right? And the observation of 't Hooft is basically that in the angular j direction, the dependence is very weak. So essentially what it ends up doing is that it suppresses one quantum number, because of which you, instead of getting a volume scaling like Planck should, he gets the 't Hooft scaling, which I call it, is area scaling. So the j dependence is very, energetically not expensive. And that's also the reason why we need a J-cut. So, and I think that my suspicion, I mean, this is just pure speculation, is that somehow some stringy effect will have to come up. It somehow has some feeling of Hagedorn and various things you could say. Yeah, go ahead. I think there's another question. No, it doesn't. J-cut and epsilon together is essentially one parameter. And that parameter, if you fix, so the one thing that I would say is that epsilon has to be sufficiently close to the horizon so that the normal modes become of this form. If they are far from the horizon, the spectrum dependence is linear in J. So you want to be sufficiently close. That's apart from that, the dependence is just purely a function of just epsilon and J-cut together.
You get the black hole entropy if you just fix epsilon to be a fixed number for all energy.
Epsilon, yeah, epsilon and J-cut both are going into the expression, but I'm saying that one combination of them is absolute constant. It doesn't depend on energy anything. Yeah, but also, you know, you should not be, I mean, I don't want to fool you too much because we are working with a fixed black hole background. So the mass of the black hole, the geometry knows about it. Cutoff doesn't have to know about, I mean, cutoff knows about the mass in the sense, well, I mean, the cutoff doesn't know about the mass is what I would say. But we are working with the background, which is the black hole background, right? So that we have to somehow put in the fact that we are working with a given sliver. So there are two places where that goes in. One is in choosing the background geometry, and the second is in the level to which, the energy to which I am filling my excitations. So these are the two places where it goes in. But once you make the choice, there is no particular, I mean, there is a lot of, you know, epsilon I can adjust while moving J-cut higher. So there is not a completely fixed thing.
This is not just a Susskind-Uglum observation, right? That you can trade an area by 4GN plus the, that's, you're doing more than that somehow. I mean, you could think of this as a cutoff that you put.
I wouldn't know how to translate that statement into this directly. That's how I would say it. So, because, see, that's more like a statement about area by 4G plus some bulk entropy is equal to, you know, the bulk entropy really plays a role. But I think there is some connection with that, certainly, because I think that, well, I mean, maybe we can talk about it later, because I think it is, you know, there are, I don't think it is quite that, because what I'm getting here is essentially just the A by 4G, right? So in a sense, it's not A by 4G plus some bulk contribution, which may be incorporatable in some way. This I don't know, but
you're saying the one loop contribution is the A by 4G.
So, yeah, so that's the thing. So I think that, you know, here I have treated the scalar as, yeah, I mean, okay, yeah, there is the scalar I am treating as free, right? Here I have treated the scalar as free. So maybe one can say more by actually incorporating interactions of, you know, et cetera, et cetera. So, but yeah, so, oh, it's over. So, okay, let me, I haven't gotten to the place where Suvrat will really criticize me. So let me get to the, let me get to that. So, this is, you know, very closely related to recent suggestion by, you know, this, I mean, I'm saying some words about type 3 algebra. As I said, I don't know much about it. My student was an expert. So, so the idea is very roughly that, you know, the single trisector of large N gauge theories, you know, they will, at finite N, they generate the entire algebra. But at large N, you basically expect that, you know, there is a phase transition, you get a type 3. Okay, instead of type 1 is the algebra of the full Hilbert space, etc. So, so the point is that type 3 algebras have non-trivial commutants, which basically means it's a candidate for the other side of the black hole, two-sided black hole thing. So it could be, so I kind of like to think of it as sort of a bulk mechanism where this sort of thing is happening, because one of the indicators that Loithoiser and Liu use is the fact that the Hartle-Hawking correlator has a, you know, has the spectrum is upward on the entire real line as an argument for this claim that type 3 algebras emerge. So that's the statement. So this is kind of what we are seeing here. So, but from the bulk side. So, yeah, so what am I saying? So, right. So yeah, so this is, you know, so we can use this algebra construction to, you know, before the page time, for instance, in the large N limit, you know, it kind of legitimizes the construction of Suvrat, you know, for the pre-page time. The part that he will not like is the part I'm going to say about the post-page time, which is where the real, this thing is. Because here, you know, on the pre-page side, you can, you know, the people who know this, there is a, you know, this half-sided modular translations exist. There is a, you know, modular Hamiltonian you can do a cross product after moving it inside and so on and so forth. I mean, you should really talk to Vaishnav. I'm not the guy. So, and that's, you can do similar things, and but it's also not a surprising fact that it can be made legitimate. So So, but the thing is, but it also provides a perspective on state dependence after the page-time in thermofield double constructions, which is that the Hartle-Hawking correlator is losing information after the page-time, right? So, but on the other hand, I would say, maybe Suvrat will disagree, is that the bulk operator that is being constructed in his way of looking at it is something like, there is a mode function. I should not write it here, I think. So there is a mode function. So this is your bulk field, if you like. So this should be OL. So this is your, let me call it the bulk field in the interior, and there will be some Hermitian conjugate. So this is in your eternal black hole picture. So you need modes going this way as well as this way. And these two modes are taken to be the Kruskal modes, essentially the Kruskal modes in your construction. So, and the challenge is basically to construct the interior operator. And then you take the Hartle-Hawking state and start from OL and construct the mirror operators and so on. So, but the thing that I would say is that if the moment you assume Kruskal, you're essentially hardwiring Kruskal time throughout the entire history of the black hole. And if you do that, I don't see a way out of escaping the correlator dying exponentially forever. And so this means that the Hartle-Hawking correlator that you're working with is losing information. And so the Leutheuser-Liu construction is somehow escaping that because they are working with a strict Largen limit. So the page time is infinite, right? So this is, maybe we can talk about it later, but I thought, since you're here, I should mention it. In the Pune thing, I did not actually, I suppressed this slide. Anyway, so the independent structure of our construct, note that this is not a statement that is directly related to our construction, but it is more about a general statement. But we came to it sort of through this observation, our explicit construction. Anyway, but I also do not have, there are various other constructions of interior operators that have come up after that. I have not studied them properly.
Chethan, the answer to this would be you don't trust the correlator for that long, right? When you get the e to the minus s.
Right.
So you just don't trust the construction not supposed to work for time of order s.
But I would say that still you have essentially an infalling boundary condition, right?
This you will get correlators that you can actually trust for that long for times of order s.
But I'm saying that the microstates basically become order e to the minus s by 2 at that time. That's my statement. So at that point, the exponential decay has stopped. So the microstate itself, we might have to, this is not the final word on the precise structure of the microstate because you need UV information. But what I would say is that it has the structure needed to stabilize the decay at that time. That's all I'm saying. So, and another thing is that, so this is, the first point here, which is that we know, for instance, in Virasoro blocks, for instance, that the decay actually stops at, or page time, explicit calculations, Kaplan and company before he left for, So that's a great paper, which is basically one of the few places where you explicitly compute the Virasoro blocks numerically, and then you find that the decay changes from that to t to the minus 3/2, which is very interesting because that's exactly what happens in spectral form factor type of calculations. So, which I think is a strong suggestion that one should not trust the Hartle-Hawking correlator even after that, So anyway, so I will just leave it here. I'm sympathetic to the notion of interior of the page time and an evolving microstate complexity. Maybe there is a way to do that. But an infalling notion of smoothness seems very difficult to allow after a page window. Anyway, so I'll comment 2, I will skip because I'm already out of time. So these are a bunch of comments, but let me leave you here. Thanks for your attention.
Chethan, yeah, one more.
About long time. What about short time? You see, you have this cutoff.
Yeah.
So if I send something from the boundary, it shouldn't bounce back too fast.
I think what
in the cutoff will kind of make it bounce back, right? So you'll see a periodicity in the boundary correlator for very short times that you shouldn't see.
See, what happens is that, like, if you, so there are 2 ways to look at it. One is that if you send something in, the time that it takes to the stretched horizon, to get to the stretched horizon, is precisely the scrambling time, right? Because you can, if you send something in, that's exactly the time that it takes there. It's not infinite time. It's precisely the scrambling time. So that, I think, in my view, is an indication that the system is finally becoming aware of the finiteness of entropy.
Order 1 time, you don't reach the horizon in scrambling time, right? I mean, in infalling observer would cross the horizon in.
I'm talking about the boundary clock. So if you're sending in, like, I'm just saying that if you look at, the dt dr equal to 0 equation, and if you just integrate it, you will find that the time that the boundary clock takes
To
for
come-
this
to
guy
mean to
to
bounce
reach the
back.
stretched
I
horizon,
see.
reach the stretched horizon, is basically precisely the scrambling time, right? So, but note that, I think that, but there's an interesting calculation there which we have not done, which is basically that you might be able to formulate things of the OTOC type of things here, which we have not done, because the correlators that we are computing are kind of mundane vanilla correlators, right? So because of which only timescales we are aware of are the diffusion time and the page time. Other than that, we are not aware of any time scale in between. But I think that, yeah, so there is other correlators which might be able to, say some things about them. But yeah, that's a good point.
Okay,
Yeah.
one more question.
Yeah.
Ronak.
If you calculate the, calculate the entropy of the exterior of a black hole with stretched horizon, it's always going to look like area times cutoff. And
Area times cutoff.
Yeah.
Yeah, so I don't know whether that's, so for instance, if we do it in 1+1 dimensions, what is the area? So because a lot of calculations are done in 1+1 dimensions. And I think that there you will get the linearity in n, but the J degeneracy will not happen.
So in that case, when 1+1 dimensions, the role of the area is played by dilaton.
Sure, yeah.
And that's related
Yeah, so but
to,
then I think this calculation is not really valid, right?
Sure. Sorry, which dimension did
The
you
one
do?
where you're putting a probe scalar and then computing
Which
its normal
dimension did you do the calculation?
I did it in essentially higher than 1+1.
Okay, so let's talk about that.
Yeah.
So there you're going to get area times cutoff, and it's always possible to tune the cutoff to 1/4 G Newton.
Right. Yeah, you're saying that the area scaling is already there,
Yeah, so-
but the precise value can be fixed by the choice of cutoff. Yeah, I agree with that.
Is it clear that how do you check that you've done something more than just doing that particular fine tuning? And maybe
Because we
another way
also,
to
well, I mean, we get the temperature, we get the some class of correlators. So those are,
the temperature is automatic, right? It's just a statement. It's just a spectrum of the cutoff theory. I think I don't know if that's non-trivial.
well, you can think that.
Yeah. No, because it's.
It might be, see, the thing is, here's what I'm saying. So there is one non-trivial fact in the calculation, which I think is the spectrum of the omegas, right? So for instance, I think is not, I don't know whether it is completely fixed. Because I don't know whether you can see that the J spectrum has a quasi-degeneracy without doing that calculation. That is not clear to me.
Okay. Maybe another way to ask the question is, okay, suppose you take a black hole with a finite interior, like not too big, not like a bag of gold, but say a collapsed black hole or something, how would your proposal for the microstate see that there's a finite interior in
So
there?
I think that's an interesting question, because I think that like somehow, we are just looking at it from purely an ADS-CFT, heavy state in the CFT point of view, right? So I think it's not clear to me how this is, I think I was asked this question before also. So I think that Samir, by the way, doesn't like this at all. Samir, I just wanted to say. So that's the impression I got. So, and one thing I felt is that he's not happy again with the same thing that you're asking, which is that, why is it that, how would you phrase the interior of a black hole calculation from this perspective? And I don't really know. But what I'm saying is that from the CFT point of view, this is the state that I have. It can reproduce the exterior, and there is a limit in which it allows an analytic continuation of the standard locking thing. Okay, so that is what that's the best I can do. But maybe there is a way to formulate this question by setting up some path integral calculation in the CFT or something, where you put some operators which can somehow be seen in the other side. But okay, those are all words.
All right, with that, let's thank Chethan again.
Yeah, thank you.